All right, back from break. Let's wrap up chapter 35. So we had gotten into this idea just before break. We had started asking ourselves what would happen if instead of having a slit opening, we had a circular opening as an aperture. And we said we'll get a circular interference pattern. So that's a circular diffraction pattern, and that comes from a circular aperture. So a little tiny circular opening in the barrier, that's what it produces. And then we want to ask ourselves, well, if I have two light sources and they're coming through some kind of an aperture, now that looks like a lens, but it's coming through some kind of an aperture, so maybe there's a pupil or even a narrower device, and maybe the image is being formed. In any case, I'm just thinking of this as an aperture, not necessarily a lensing device. What we find is the path from one of those objects is going to have its central maximum here, and then it will be surrounded by some diffraction fringes. The second object will have its peak here and be surrounded by some fringes. Now, if those two central maxima, they're not at one point, if those overlap enough, I'm not going to be able to tell that there are two objects. I can only tell that there's one blurry object. I can't tell if there's two or not. And that's called resolution, limits of resolution. So the definition, now this is kind of an official definition of when can we resolve two images and when can't we. But for two slits, what we say is, well, for two slits or for the circular aperture, for either one, what we say is when the zero from one of those overlaps with the peak of the other one, and vice versa, we are at the limit of resolution. So think of, here is the central peak coming from one of those objects. So that's the light coming from one of those objects through the slit. For that object, the center of the screen is here. For the other object, for O, the center of the screen is here. For O prime, the center is here. There's a very small angle between them, and so I'm getting an overlap of the central maximum. Now, if it's two slits, then the zero from one of those would be at n equals 1, and the, boy, I hope we got all these right. Let's see, n equals, yes. So for object O, n equals 1 is here, n equals 1 is here, n equals 0 is here. For object O prime, m equals 0 is here, m prime equals 1 is here, m prime equals 1 is here. When this condition is met, we are at the limit of resolution. If they get any closer, the two objects blur together, is what we say. Now, of course, if you're data collecting, you're trying to do your best to still resolve these, but this at least gives us a number to work from. Now, for two slits, this would be the case, the m values. If it's a circular aperture, and we're using 1.22 lambda over d, then this is 1.22, and this is 1.22, and this is 1.22, and this is 1.22. So the numbers shift depending on whether the aperture is circular or whether it's a slit. But in any case, that raises an important question about how reliable imaging can be, or how reliable is imaging using a telescope, how reliable is imaging using our vision. And to start with, they bring up the Hubble telescope. Now the Hubble telescope, you would think would not have a serious problem with this because it's pretty wide, right? If we have a really wide sample of light coming in, that should minimize the effect. And so what we're going to do is we're going to pick something right in the middle of visible light, something in the green part of the spectrum, and we're going to give it a wavelength of 550, and say if I've got light coming into the Hubble telescope, and you guys know what the Hubble telescope is, right? The Hubble telescope's been up there, how long has the Hubble telescope been up there now? 25 years? 30 years? Best investment ever. So if you look at pictures from the Hubble telescope, just remarkable, all the things that the Hubble telescope has been able to image thanks to being up above Earth's atmosphere. So anyway, the Hubble Space Telescope that's in orbit around the Earth, up above the atmosphere, so the atmosphere is not limiting its resolution. So let's take a look and say, well what about diffraction effects? Now, the objective lens has a diameter of 2.4 meters. And so let's go back and look at this. Oh, that's true. That is a diameter, isn't it? So, yeah. All right, so what we can do is we can use the circular aperture formula. I just realized if we're comparing M values for the circular aperture, this is a diameter, not a radius. If we put a radius in here, that's gonna, if we divide top and bottom by 2, that becomes a radius, that becomes 0.61. So I guess the M value would be 0.61. That's probably something you guys weren't that concerned about. But if that was worrying you, you won't have to lose sleep over that. I think we've got that factor of 2 taken care of. So the diameter here is 2.4 meters, and let's see what kind of limits to resolution we have. Now, this is a telescope, and so what we're trying to do is image objects that are very, very far away, and if I've got objects very, very far away and very close to each other, well, let's take a look and see. So here is the limit of resolution. It's going to be given by 1.22, the wavelength over d. And what they told us is the wavelength, let's think about the green central part of the spectrum, 550 nanometers, and the diameter of the sample of light coming in is 2.4 meters. Putting all those numbers into my limit of resolution formula says that, now this is going to give us radians. So just to be clear, we put lambda and d in the same units, the units cancel out, and the answer is in radians. So if you want to put this in degrees, if you've got a homework problem or a midterm problem, and it says, what's the limit of resolution, and it asks for degrees, you got to do units conversion. So naturally, this equation is currently set up for standard units, and standard units are radians. So the angle we get is 2.80, 10 to the minus 7 radians. That's pretty tiny. So that means that when the Hubble telescope takes images, that level of resolution, we can't do any better than that due to diffraction. Now I think with the Hubble telescope had, I think this is an accurate report on this. You guys have to let me know if this is true, but I think there originally were images of Pluto using the Hubble telescope where they first saw evidence that Pluto had a moon, that Pluto was actually a double system, a double planet system, so it's really two pretty good sized objects orbiting each other. And the issue was, well, at what point can we confirm that there are two objects there, and when is the blurriness not allowing us to decide that? And I'm trying to remember if the Hubble telescope was able to resolve it or not, but I remember specifically these kind of blurry images that looked a little oblong, and the argument was there are two objects there, and the images are overlapping due to, say, diffraction limitations. Now, this is the limit due to diffraction, and so what I did was I just looked up and online. I said, what's the atmospheric resolution limit? Or maybe this was part of the problem. Let's take a look at that before yes, this was part of the problem. So it's a good thing I caught myself there. The resolution limit due to Earth's atmosphere, that's the best picture right there. That's the one we should just be looking at. I really do like that. Look at that. Look at the planet. Nice picture of the planet. All right, back to work. And so the atmospheric resolution, they say, is about a half second of arc. Now, if you know angular measure, 1 degree is about 0.0174, well, 0.01745 radians. 1 minute of arc is 1/60 of a degree. This was not my idea to define these units. 0.000291 radians. 1 second of arc is 1/60th of a minute, which is 1/60 of a degree. So at 1/3600th of a degree, that is 4.85 10 to the minus 6 radians. So that resolution is better. So the limit of resolution from diffraction with the Hubble Space Telescope is less of an issue than atmospheric resolution limits. Okay, so even with this modest size telescope, so the Hubble telescope, you know, it's not big like the Earth telescopes could be. I don't know, what are the big telescopes now? 10, 20, 30 meters across, something like that. And this is only at 2.4. It's a much more modest sized telescope. Still, 2.4 meters, that's a pretty good size. But its diffraction limit, because of its limited size, is still much better than what atmospheric limitation would have done for a telescope back on Earth. One more look. Sorry, I just had to look one more time at that picture. Okay, so if we're looking at human vision, let's say you're in an airplane, is what this problem says. You're at 10,000 meters, 30,000 feet, 31, 32,000 feet, and you're looking down at the ground, and you're trying to decide how good is the resolution. Can I, at 10,000 meters, can I pick out individual houses? Can I pick out individual cars? Can I pick out individual trees? How good is the resolution? Well, let's take a look at diffraction. Now, diffraction is not the biggest limitation for human vision. Just to be clear, this is not the most serious issue, but let's again take the central green part of the spectrum, 550 nanometers, and let's say that your pupil is at 3 millimeters. All right, there's the setup. So here is something on the ground. Here is something on the ground. Let's see if we can, what the smallest distance is, what's the smallest value of h that we could resolve. So the way that's going to work is, first of all, let's see what the limit of resolution is for human vision based on 1.22 times the wavelength. The wavelength we're using is 550. What's the circular diameter of the eye? That is 3 millimeters, so 3 times 10 to the 6th nanometers. And when we carry out the calculations, we get 0.000224 radians, or 2.24 10 to the minus 4 radians, or 1/100th of a degree. So based on the diameter of the pupil, if that's the only limitation you've got in your vision, you should be able to resolve objects with an angular size or an angular separation of 1/100th of a degree. Let's see what that is. So this is one of those slides where I did the stuff on the right first, and I'm coming back over to the space that I left. Here is the limit of resolution, and we are 10,000 meters out. So what we'll do is we'll say the limit of resolution then, this angle, we've solved for it looking at the retina and the pupil, or looking at the pupil size and the wavelength. Now what we're going to do is work the problem in the opposite direction and say theta is equal to h divided by d. Again, we're using that small angle radians definition. So that's the angular size, or the angular separation. Theta is given by h over d. So using that formula, I can solve for h. H is equal to d times the limit. Now this is already in radians, So I just want to use that. So it says at 10,000 meters, if it's the diffraction limitation would limit me to being able to resolve images that are 2.2 meters from each other. So if diffraction was the only issue, you could look down and pick out objects that are separated by 2 meters. Now there's other issues with human vision that are more important. So, and those issues are, what's the curvature, how perfectly curved is the cornea, and how perfectly curved are your lenses within your eye. Those are a couple of concerns, because what we find is actually opening up the pupil, you know, having the pupil open up to see something actually makes your vision blurry. It doesn't do better. And the reason why is, if your pupil opens up, you're using a wider part of your cornea and a wider part of your lens, and the curvature along the lens and the cornea is less than perfect. And so you actually run into bigger difficulties. When I was a kid, I would be in, I maybe told this story before, but when I was a kid studying, my parents would come in and they'd go, turn some lights on. You're in a room, there are no lights on. How can you see what you're reading? And I was fine. But then years later, what I found out is that the curvature of your cornea, the curvature of your lenses kind of degrades as you get older. And now that I'm older, I have the same thing happen. I think, oh my gosh, I can't see, I better turn on some lights. And turning on the lights makes my pupils get narrower, and that means I'm using not as wide a range of my cornea and my lens, and the images get sharper. All right. So anyway, diffraction's not the main concern, but it's kind of interesting to go in and see for a, what was it, a 3 millimeter pupil? Yeah, for a 3 millimeter pupil, that predicts 2 meters as a resolution limit at 10,000 meters in an airplane. All right, here's another example here. Ooh, we got to get moving here a bit, huh? Here is 2 theoretical calculations. Maybe I will bypass this example. Let's see what we've got. I might move through it quickly. So we've got what's a 200-inch telescope in Southern California on Palomar Mountain, and then there's a radio telescope in Puerto Rico with a radius of 300 meters. How do the angles of, how does the resolution compare? What is the theoretical minimum angular separation of 2 stars with these 2 telescopes? So let's do a comparison side by side. First of all, here is that radio telescope, and that radio telescope, they're telling us, is 300 meters across. So this Arecibo radio telescope is 300 meters across, and I noticed in the news, not too long ago, maybe earlier this year, maybe last year, that this has kind of gone into disuse and that disrepair, and that the collecting mechanism here at the top for this radio telescope collapsed. The cables were failing. They applied for more funding. They didn't get it, and it was allowed to crash down onto the disk. It could be rebuilt at some point, but I think for now this telescope, unfortunately, has been abandoned. Okay, but we have other radio telescopes out there. We have arrays of radio telescopes. Let's see, so for this example, we're going to be using the circular aperture. We're going to start with the visible light from Mount Palomar telescope with a wavelength of 550 nanometers. For the radio telescope, they tell us to use a wavelength of 4 centimeters, quite different. The diameter here, it's referred to as the 200-inch telescope, but of course it should be the 5.1 meter telescope, so 5.1 meters. The radio telescope has a diameter of 300. Plugging all the numbers in for the Mount Palomar telescope, we get a resolution limit of 1.3 10 to the minus 7. The Arecibo radio telescope, the resolution is not nearly as good. That resolution is about 1,000 times finer than this is. Now with radio telescopes, you can see, because the wavelengths are so large, to limit the diffraction resolution issues, you have to get a huge dish, or you can use arrays. You can set up many smaller radio telescopes, and I think there's an array, what is it, the very large array is in New Mexico or something, and they can move these radio telescopes around to create the effect of a much larger telescope. So anyway, the limit on the visible light comes in at about 1/100,000th of a degree, and the limit on the radio telescope, that's still pretty good. 1/100th of a degree, that's remarkable resolution for a radio telescope. Okay, here's a next topic that we want to look at. So in chapter 35, what have we looked at so far? We looked at diffraction in a lot of detail. So we looked at diffraction in a lot of detail. Take a look at the homework problems. I think they're mostly going to follow up with what we've talked about conceptually. And for the most part, you can work from the formulas we've derived. As always, make sure that you're talking yourself through problems and that you have a conceptual understanding of the calculations that you're doing, of the formulas that you're working with. Now, after looking at diffraction, then we brought back two-slit interference and showed what diffraction and two-slit effects combined looked like, and we looked at that in a fair amount of detail. And then we moved on to this limit of resolution, okay, and so we've wrapped that up. We have a couple topics left. One of them is diffraction grating. This is also an interference effect. Now what happens is this, back when we had two slits, back in chapter 34, we had this gradual rise and fall in intensity across the screen. Well, what happens if instead of two slits, what if we get 6, or 10, or 20, or 100, or 500 slits, or 1,000? What's going to happen? Well, let's start with 6, because that's the diagram they've provided. If I have 6 slits, what we can do is go through and show I still get peaks at the m=1 values, but the peaks are much sharper. And the reason why is with 6 slits, it's much more difficult to get these slits all lined up. It's much more likely that 6 slits end up with kind of a random set of, a more random set of interference effects, and they tend to cancel each other out. So this is good news if we're trying to guide light in a particular direction. What we can do is we can create what we call, okay, the name is really confusing. These devices with many, many slits, many more than 6, are called diffraction gratings, but they're not based on diffraction. They're based on multiple slit interference. So that's what I'm going to say. This is an effect due to many, many slits all lined up together. It's not due to the stuff that we've been talking about as diffraction. Just for historical reasons, that's what it got called. Now, what's going to happen then when we get many slits together is we're going to get lots of really low intensity, lots of zeros. So if we have 6 slits, for example, we'll have a 0 at n=1/6, 2/6, 3/6, 4/6, 5/6, and then at 1 we get a peak. So if I have n slits, I will have a bright peak, and then I will have n-1 zeros, and then I'll have another bright peak, is the way it works. So what happens here is, if we were to, with the diffraction grating, we get to keep using the formula d sine theta = m lambda. This formula works for any number of slits. It worked for 2 slits, it'll work for 10. It'll work for 100. Now what happens here though is that when we're sending light through a diffraction grating, let's say that we send light that is monochromatic, there's just one wavelength in that light that we're using, and it's at 400 nanometers. Well, if I have one wavelength of light at 400 nanometers coming through, and I've got many, many, many slits, what's going to happen is I'm going to get a peak here at n equals 1, and a peak here at n equals 2, and a peak here at oh, they didn't include, oh, they didn't include 3. Okay, 3 is going to be out here somewhere. So instead of getting the light gradually rising and falling, I get a series of sharp peaks. Remember, that picture was for six slits, but my diffraction grating, my multiple slit device, is going to have hundreds and hundreds of slits, maybe thousands. Now, if I send the entire spectrum through, what happens is I create a rainbow. So I'll get all of the n equals zeros land at the same place. But what will happen here is, well, the blue at 400 nanometers will land over here. The red at 700 nanometers will land over here. But now I've included all of the wavelengths intermediate between those values, and that means each of those will show up. And because this is a multiple slit device, a diffraction grating, what's going to happen is the wavelengths are actually going to get sent into a fairly narrow region. You know, each wavelength kind of lands at one spot, and so this really sorts out light based on the wavelength. So we can take light from a source and find out what wavelengths are present. Let's say that this is coming from looking at a light source. Well, what the diffraction grating is telling us, what the multiple slit interference is telling us, is that this light really only consists of two different wavelengths. Some of the light is 400 nanometers, and then there are 700 nanometer photons present, 400 nanometers, and they're being sorted out. Down below, what that's showing us is that I'm getting the whole spectrum of visible light because all parts of the spectrum are filled in. This allows us to sample light from, let's say, stars. So I can look at a star, and I can look at the light, and within that rainbow, within that spectrum of light, what we're able to see are specific lines that show up. I think we've got some examples, we'll get to those, that tell us what compounds or what elements might be present in that star. Anyway, let's take a look at this example. It says that we have diffraction grating lines determine the angular positions of first and second order maxima for 400 and 700 nanometers. The grating contains 10,000 lines per centimeter. So this multiple slit device has 10,000 slits per centimeter. Now, they actually don't have to be slits. What they can be is just etchings within the diffraction grating, within the multiple slit device. You can work with etchings. So if you just have furrows that you've etched into the diffraction grating, that will create the interference effect. CDs, if any of you still have CDs, if you remember CDs, when you used to play music off of CDs, you could hold them up to the light and you could see the rainbow coming off of those CDs. Now this grating has 10,000 lines per centimeter. Let's see what its properties are going to be. I want to find out what the D value is. To find out the D, I take the 1 centimeter, divide by 10,000 lines per centimeter. That'll give me a D value in centimeters, but I want that in nanometers, so I'm going to convert into nanometers, and that gives me a D value of 1,000 nanometers. So the etchings on this diffraction grating occur every 1,000 nanometers as we scan across the diffraction grating. And here it is. Here are all these little etchings or slits that have been produced. Now what's going to happen is we'll have a first order spectrum that runs from 400 to 700 nanometers, and then we'll have a second order spectrum that runs from 400 to 700 nanometers. For the first order spectrum, m is equal to 1. For the second order spectrum, m is equal to 2. And then, did we do a third order? I don't think we did. Okay, so for the first order spectrum, what we're finding is that the blue end of the spectrum will come in at 23.6 degrees. The red end will be at 44.4. So this is from 23.6 to 44.4 degrees. That's going to be the first order spectrum. Now for the second order spectrum, we put in m is equal to 2. Here we had m is equal to 1. And now the blue starts at 53.1 degrees, and it continues all the way to, red, it turns out does not have a solution. And that's because 2 times 700 is bigger than 1,000. So we never get to this, okay, this diagram then is incorrect. So the first order spectrum, we got the complete first order spectrum from this diffraction grating, from this multiple slit device. The second order blue, the second order spectrum started. I got blue, but then I hit 90 degrees before I got to 700 nanometers. So we can back solve and ask, well, how far did we get? At theta equals 90 and m is equal to 2, the wavelength that we get to is only 500. So it says that the second order spectrum for this particular multiple slit grating goes from 400 to 500, and then we run out of angles. We're at that point, we are at 90 degrees. Okay, I think that's everything in this example. Let's move on. What about spectral overlap? What happened here, notice that the blue and the red, first order, did not overlap with the second order. Well, that's not necessarily true for all orders. What's happening here is it comes down to, the blue is at 400 nanometers, the red is at 700. So it comes down to what range of wavelengths we're working with and the m values. So what we'll find is that they've given us a different grating. This one is 4,000 lines per centimeter. Now the overlaps don't really depend on the d value. The overlaps just depend on the wavelengths of light and the order number. So it depends on what the value of m is, and it depends on what the wavelengths are. So let's go ahead and use this. Here is my multiple slit grating, the diffraction grating. Here's a bunch of those slits. Remember d, or maybe we didn't mention, d is the distance between each slit. So we're going to have hundreds or thousands of slits, and d is the distance between each one. In this case, they say every centimeter is divided up into 4,000 slits. So 1 centimeter divided by 4,000 gives us, when we do some units conversions, 2,500 nanometers. That is the d value. Now what we can do is, let's look at first order for blue. M is equal to 1, wavelength is 400. Solving from this equation, it says the first order spectrum will go from 9.2 to 17.5 degrees. Okay? And these diffraction gratings are just a miracle because it lets us sort the light out and see what wavelengths are present. When we do the second order, we end up with 18.7 to 36.9. Now the reason there's a gap is because 2 times 400 is bigger than 1 times 750. Oh, and then we're using the value 750. So they're saying this time for the red light, yeah, go all the way to 750 nanometers for the wavelengths of the red light. So we're going from 400 to 750. Now when we get to the third order, notice that 3 times 400 is not as big as 2 times 750, and that means we'll get overlap. So there is overlap. The blue third order starts before we're finished with the second order. So if I want to be able to use a diffraction grating and be able to see a clean sample of visible light showing up, I have to stick with first order, because with second order, I'm going to start seeing overlap. And then when we get to fourth order, I'm not sure if they asked for this, but I went to fourth order, and that started at 39.8, so that's well into the third order. And then we didn't reach the fourth order. because when we got to 90 degrees, the fourth order, the largest wavelength for fourth orders, it ended at 625. Okay, so that's mapping out the wavelengths, the range of wavelengths that will show up in a particular diffraction grating in a problem. And this is what I was talking about. So these are spectral lines. So what happens is we can take light coming from a star, for example, or from, I think this is just from a, yeah, this is a thin gas. This is more like a, here we go. So the star spectra are absorption. So the light coming from the sun looks like the whole spectrum, except that there are some lines that are missing. And the lines that are missing correspond, well, some of those lines correspond to the presence of sodium. The other line here corresponds to the presence of hydrogen. Helium, hydrogen had better be in there, and helium too. So anyway, this is what diffraction gratings are capable of doing. In your chemistry classes, if you've taken chemistry classes, they will do infrared spectra. They'll do absorption of infrared to look at different molecules and try and figure out what the compound, what its configuration is. Different chemical bonds tend to absorb photons of different energies, and vibrational and rotational energies in molecules show up in the infrared spectrum. So you can do infrared diffraction gratings. Now here is the hydrogen spectrum, and here what we're saying is that we've got 10,000 lines per centimeter, and we are seeing in this hydrogen spectrum, oh, they don't have a nice picture. I think we have to go back to this. So if you look at that hydrogen spectrum at the top, there are 4 distinct lines in the visible part of the spectrum. And let's find out what those wavelengths are by sending it through a diffraction grating. And so what we can do is say, here is light coming from a sample of hydrogen. So we've got hydrogen, maybe we're sending an electric current through hydrogen, the hydrogen atoms are glowing, and we want to say, that hydrogen light looks maybe kind of like it's kind of reddish or violet red. What wavelengths of light are present? And so we can take the light from that glowing hydrogen, send it through a diffraction grating, and what we find is, within the visible spectrum, there are really just 4 distinct wavelengths that show up. And that turns out to be a very particular indicator of the presence of hydrogen, or that the light was generated from some glowing hydrogen. You'll see these pictures from space where you have regions of hydrogen gas near really high temperature stars, and the region of just hydrogen gas is glowing. If we take a look at that light coming from those clouds of hydrogen gas, we'll see these 4 lines. Now the D value, this time they said it's back to 1 centimeter divided by 10,000. That gives us a D value of 1,000 nanometers, and we're going to look at the first order spectrum where we can reliably pick these out. We're using our old friend d sine theta equals m lambda and solving for the wavelengths. So in our diffraction grating, which we understand to have a D value of 1,000, put that in. All we have to do then is look at the angles and then calculate each of the wavelengths. And those are the 4 very prominent wavelengths in hydrogen. Once we get into the quantum mechanics of atoms, we're going to be able to derive those 4 wavelengths. We're going to be able to show where those 4 wavelengths of light come from in hydrogen based on the interactions of the electron and proton. Okay, something to look forward to, I hope. So we're into the last topic in the chapter, and this is the topic of polarization. This is the one that we mentioned at the beginning of the chapter. And this is an interesting property that fundamental particles have. So photons have the effect of polarization. Now what they're showing here is one analogy to this would be that the electric field within light can either be vertically oriented or the electric field can be horizontally oriented as it propagates. So the direction of propagation is along this line, and the E fields can either be lined up vertically or horizontally, or more generally, it's a combination of both. And so we say that there's two possible polarizations, and let's take a look at a device that allows different polarizations to pass through. So what we're saying here is that we have some light, it's incident. There can be light along the X direction. I think Z is the direction going through the polarizer. There's going to be an E cosine theta component in the Y. There's going to be an E sine theta component in the X. Now that's a vertical polarizer, and what they're saying with this is that the polarizer only allows vertical light to pass through. So the X component of the electric field will not pass through, and all we're going to get out of that is a cosine theta component. Now let's look, this is probably a good place actually to start here. Let's say that we start with unpolarized light. Unpolarized light means that if we sit there and sample the polarization effects within the light, it's just random. If we have a device out that can pick up, that can measure preferences for vertical or horizontal polarization, they are equally being activated. So it's a 50-50 combination in some sense of vertical and horizontal. Now actually, quantum mechanically, what we say when we get into quantum physics is this polarization is based on the spin of the photon. And so when we just randomly generate photons, they haven't decided which polarization state they're in. They haven't decided if they're vertically polarized or horizontally polarized. And so it's actually a superposition of quantum states up until the photons run into a polarizer. Polarizers are designed so that they have molecules that are kind of strung along one direction, where it's easy to absorb electric fields that are in one direction but not perpendicular. Now what we've got here is this is a vertical polarizer, meaning that the horizontal component gets taken out. So you can think of this as like if I'm riding my bicycle along and there are gratings in the gutters where the water goes down into the drainage systems. If the gratings are along the direction I'm riding, I go right through. Oh, that's not a good thing though. But if they're perpendicular, I'm safe. And I get blocked, which is good. So in this case, the horizontal ones get blocked by this system of the polarizer, and the vertical ones get through. Just be aware that textbooks vary by what they mean by these vertical and horizontal lines. Sometimes they mean the vertical ones get through, and other times that means that the vertical ones get absorbed. And the reason for that is if these are little metal conductors, lines of metal conductors in the polarizing device, that will absorb microwaves, for example. So a microwave polarizer will actually, with vertical lines of copper, will actually absorb. So in a sense, this could be backwards. Don't get attached to this particular picture. So if we allow the vertical polarization to come through, that removes half of the photons. Half the photons, when the photons get to that point, they have to make a decision. Am I vertically polarized or am I horizontally polarized? I have not committed up until now, but I'm running into this polarizer. I have to commit. That's it. And so they flip a coin, and if it comes up heads, then they're horizontally polarized and they get absorbed. If it comes up tails, then they pass through. Now, they don't really flip a coin, but quantum mechanically, there's a probability of those possibilities happening. And if the light was generated in a non-polarized fashion, just randomly, then it's a 50-50 chance that they'll be absorbed. Now, if I rotate the polarizer, by any angle, and I come in with unpolarized light, half of the light is going to go through and half of the light will not. So it's not specifically horizontal and vertical, it's any two perpendicular, or what we call orthogonal polarizations. Any two polarizations which combined represent a pair of possibilities that are either one or the other. Okay, so it could be vertical and horizontal, or it could be diagonal this way and diagonal this way. That's an alternative version. Now if I take a second polarizer that's tipped horizontally, that removes everything. Okay, let's look at a couple more possibilities here. Here we have two Polaroids. They're angled at 60 degrees relative to each other, and we're going to start with unpolarized light. So here's a good way to organize your diagrams. This is unpolarized. Both polarizations are present, and both polarizations are present in equal amounts. In fact, the individual photons haven't even made up their minds, so it means that both polarizations are still equally likely for each of the individual photons. So these photons come up to a polarizer, and again, since this is unpolarized completely, it doesn't really matter how this is oriented. Let's say it's oriented vertically, and that the vertical polarization gets through. Well, that represents half of the photons. So no matter how this first one is oriented, if this is unpolarized, the intensity is down to 1/2. Half the photons were absorbed, half were not. Now, if this had been tipped at, say, 35 degrees, then the polarization of the light coming through would be exclusively tipped at 35 degrees. So once the photons have made up their mind as to whether they match the polarizer or if they're perpendicular, the photons coming through match the polarizer. Okay, now they're in a definite state of polarization. Now if we get to a second polarizer that is at some angle theta compared to the first one, that means that this polarizer is at an angle theta relative to the polarization direction of the light. That light was unpolarized, but now that we've gone through a polarizer, this is completely polarized in some direction. It could be vertical, it could be horizontal, it could be tipped at 40 degrees. It all depends on what the orientation was of that first polarizer. But that light coming through is going to be locked into one polarization, and it can be at any angle. Okay, now what happens with the next polarizer is the important question, is how is this polarizer rotated relative to the light coming in? This light, if it's completely vertical, and this one is tipped at 60 degrees, that introduces a factor of cosine squared. Now the cosine squared is happening because the component of the electric field gives us a factor of cosine of 60, and the intensity depends on the electric field squared. So the component is cosine 60, and the intensity is the cosine squared. So I'm going to keep that factor of 1/2 from the first polarizer. That hasn't changed. But now, because of the second polarizer, I have an additional factor of cosine squared theta. Now the numbers they gave us was 60 degrees, and so it says that that's another factor of, oh, that's 1/4. Okay, is that right? Cosine of 60 is 1/2, right? Yeah, 1/2 squared is 1/4. So 1/2 of the light gets blocked by the first polarizer. Of the remaining light, 1/4 of it gets through. So I'm down to 1/8 of the original light. Okay, what happens if we put a number of polarizers, 3 polarizers, right in a row with each other? If I put 3 polarizers right after each other, what's going to happen is, in this lower picture, half of it's going to get, we start with unpolarized, half of it gets through the first one, and that's vertically polarized. Now the last polarizer is horizontal, right? So you would think if this is vertically polarized, eventually that's going to get blocked by this last one, but it doesn't. And that's because the intermediate polarizer is rotated at 45. Now this seems kind of, I don't know if it's unfair or it doesn't seem to be following, there must be a rule out there. What we're doing is we're taking light that's vertically polarized, sending it through a polarizer at 45 degrees, the light coming out tips. Only half the light makes it through, but the light that does come out is now tipped at 45 degrees. So what just happened is that the first polarizer removed all the horizontal component, but the second polarizer regenerated a horizontal component. There's a horizontal component that came back. And, you know, the photons are just following the rules from quantum mechanics. So if you look at quantum mechanics and how spin properties of these particles behave, that's what's predicted, is that once you're in a particular state, it can be broken up into two states. And so the series of rotations here, as long as we don't have consecutive polarizers at 90 degrees, some of the light will always get through. So we can gradually rotate the light in that bottom row. It's kind of interesting. What we've got is unpolarized light will always reduce to 1/2. And then this is an example of cosine theta squared and cosine theta squared. The theta for that middle polarizer is 45 degrees. The theta for the final polarizer is also 45, because the thetas that we use are the relative angle between the light coming in and the polarizer. The light coming in here is vertical, polarizer is tipped 45. The light coming in here is tipped at 45, but the polarizer is at 90. So there's a relative shift of 45 degrees. It's tipped 45 degrees here, tipped 45 degrees here. That's how nature works. Okay, and there it is written out. 45 degrees and then another cosine of 45. Now another thing to realize here is, oh, this is, oh, we have a couple more. Light coming from the sun, when it reflects off a surface like the water that we have here, the light coming in is generated in a very random fashion. So the photons coming in are equally likely to end up with one polarization as another. But what happens is when they hit a horizontal surface, they tend to retain the horizontal component but lose the vertical component. The vertical component tends to go into the water, so the light reflecting off a surface, off a shiny surface, is largely horizontally polarized, and so Polaroid glasses are designed to take out the horizontal polarization. If I'm looking at the surface of water, if I'm looking at a shiny bumper on a car, most of the glare that we encounter is horizontally polarized, and Polaroid glasses preferentially remove the horizontal component. Now another thing to be aware of is with the sky, the molecules of air in the sky also polarize sunlight. So if I'm looking right at the light from the sun, that's got both polarizations present. But if I'm looking away from the sun, I'm looking at light that ran into some air molecules over here and then came my way. And if the light hit a molecule and scattered at a sharp angle, then that preferentially picks out the polarization shown in this diagram. So here's the light coming from the sun. It hits an O2 or an N2 molecule, and it's easy for one of the polarizations to scatter, but the other polarization gets suppressed. So if I take my Polaroid glasses and I look away from the sunlight and rotate them, I can see that there's a polarized angle with that light. Finally, I mentioned this earlier, but polarization, this vertical and horizontal polarization, actually derived from the spin states. So not only do photons have polarization, Electrons have polarization, protons, neutrons are polarized. They consist of two possible spin states. Now, the kind of the natural basis to think about these polarizations in for particles, for spin states, is what we call left circular and right circular. Again, in your chemistry or in your biology classes, you may have done labs where you're looking at molecules. As you know, what is it? All the amino acids in nature are left-handed, and all of the sugars are right-handed. We have all these chiral molecules, right? And they will rotate light. So you can send light through a sample of chiral molecules, something that has a preference. They have a left-handed and a right-handed form to them, and you can actually rotate the circular light. So the spin states line right up with left circular, right circular, but if we combine left and right circular, there are two possible ways of combining them. One of those results in vertical polarization, the other one results in horizontal. So we can work in either case. We call these two different bases that we work in. We can either work in the circular polarization basis, or we can work in the linear polarization basis to describe these states. Okay, interesting property with this spin and the polarization effects that it creates. All right, any questions you guys have? We're kind of through these 4 chapters on light. So whatever questions you guys have, definitely stop by. We're wrapping stuff up with light right now. We are going to head into special relativity and quantum mechanics of atoms and molecules. That's where we are headed.